Okay, I think we're going to get going. We can try to debug this more later, but this is why we have backup hosts. So hi everyone. Welcome to the keynote session of Haskell Symposium today. It is a great delight to introduce Mathieu Boesflug. I hope I pronounced that correctly. Maybe.
Pretty much close enough.
Okay, close enough.
Boesflug.
Who is the CEO of Tweag, where declaration of conflict of interest, where I also work. He's here today to talk about functional programming and linear types and sort of Tweag's journey through these different ideas. So thanks very much, Mathieu, for coming to Haskell Symposium, and take it away.
Well, thank you very much. It's a pleasure to be here. And well, let's see if this works. So when I was first taught Haskell, that was 15 years ago. I was told that the int-integer distinction was a mistake, that this was a design flaw in Haskell 98, that there should be only one integer type. And it should be the ideal integer type, matching the intuition that a mathematician might have of what the set of all integers should be. And this is a fine view of functional programming. The way I see it, it's about abstracting away the inessential details that are mere artifacts of present-day computing devices. You could say it's about escaping the Turing carpet and reasoning in a world of infinites. And it's pretty convenient. Infinite integers, infinite memory, fast enough CPUs, predictable performance of integer arithmetic doesn't matter too much, and so on and so forth. So this talk, though, is about how I became much more interested in another view, the notion that functional programming is a darn good way to program actual computers by being very explicit and intentional to the compiler about what we want as the programmer. One important distinction between the world of ideal integers and the real world is that the real world is finite. Running a computation requires resources like memory, like file descriptors, like sockets, like database handles, like security tokens, like money. And the finiteness of these resources means that we need some level of control on how we use them. It means that it can be a good idea to ask the programmer to be much more precise about their intentions. If they know they are working with small integers, they can tell the compiler that they know. If they're allocating lots of small chunks of memory, they can tell the compiler exactly what should be freed when to avoid running out of memory. If they're implementing complex protocols, they want to tell the compiler that their code is intended to have good resource hygiene, and therefore that the compiler should yell very loudly when they're modeling, for example, pizza delivery as pizza duplication. So to borrow from Baudelaire, who's a French poet from the 19th century, there are abstractions or ideals, and in present, but programming also means getting down and dirty with the machine. So there's a component of spleen, as he called it. And I'm interested in the type of programming where you really do want to be explicit about all kinds of computer-specific details. I'm interested in the gritty details of CPUs, network cards, and memory to make the most of them. I guess you could say I'm interested in the spleen of reality, and the reality where everything is finite and integers come in different sizes. I think functional programming is a great way to talk about reality, actually, about the spleen of it, even. And at the same time, I'm also interested in type of programming where we can build new abstractions that are not leaky abstractions. For example, when I'm implementing a pizza delivery protocol that I mentioned earlier, pizzas are resources. There's a finite number of them, And when one person has one, then the other person doesn't. Duplicating pizzas doesn't make any sense. So if I'm implementing a pizza delivery protocol, then it would be really great if I could model pizzas in my code in such a way that they cannot be duplicated. So I'm interested in getting closer to the ideal of a pizza in my code, or rather to build abstractions that that model relevant aspects of this ideal depending on my problem domain. And so over the past 5 years, there's a number of people that worked on a project to bring linear types specifically to Haskell to address these things. And so I worked with a number of colleagues at Twig and with academics like Jean-Philippe Bernardi, who's going to talk about linear types as well tomorrow. And as I said, to work on both aspects to enable a more explicit style of programming in Haskell that's more aware of the underlying machine and operating system, i.e. the spleen of programming, and to enable programming to more accurately or more completely model certain ideals, like the idea of a pizza or the idea of a file alongside the idea of an integer. The way we did this is that we went about retrofitting linear types to Haskell, and that posed a number of challenges in of itself. And I'm not going to get really into that in this talk. You know, I'm kind of the token industrialist here, and so I'll talk about the motivations from the perspective of the industrial use cases that we had for all this. So here's a picture I lifted from a presentation made by Dick Seitz, who's an engineer at Google in 2015. And so each rectangular box here represents a rack, each containing about 60 servers. It represents what, at the time, happened it's representing what happens whenever a user makes a single search query. And the query is received by one server, and that begets requests to a number of other servers. And those requests are in green, and those in turn lead to other queries, which are in blue. And in fact, Dick Seitz in his presentation says there was even a third generation of requests, but if you represented all of them on this graph as well, then it would be nearly impossible to make out any single arc. At the lowest level, the requests take a few milliseconds to yield a response, which in turn make their way back up the request graph. And the total wall clock time spent for a search query, start to finish, is about 200 milliseconds. So the overall time budget is very low. And in fact, this time budget is low for a reason. Faster search directly translates into users making search queries more frequently, and therefore into more ads being served, and therefore more revenue for Google. The effective latency on user traffic is very well studied and is directly relevant to a lot of web services. You know, this is not just about search engines. So 15 years ago, Amazon found that for every extra 100 milliseconds of latency experienced by users, they lose just over 1% of revenue. And at around the same time, Google said in a presentation, I think it was the same year, 2006 or so, that if they add 500 milliseconds, they lose 20% of their users. And then more recently, in 2017, just to cite another study, a little bit more recent, Akamai says that for every 100 millisecond delay in website load time, for an e-commerce website, the conversion rates typically drop by 7%. So for a lot of people in the industry, lower latencies means more dollars. And that's a very important constraint when designing systems. It's a constraint that means you can't just keep average latencies low, but indeed the latencies of all requests, or at least say 99% of them or 99.9% of them, have to be pretty low. Because in order to achieve these very low latencies for all users, as we saw earlier, for a single query, you're typically going to have a bunch of sub-requests that are going to be sent to a number of systems and a number of machines. And so it's really important that what's going on under the hood, the request for these requests has a consistent latency. Here's another graph of the same search query that we saw earlier. And it's a timeline showing a request coming in, which in turn gives rise to 93 parallel requests. And two of these 93 requests are taking a particularly long time. And that penalizes the performance of the system as a whole, because we can't construct a response to the initial request until we have all responses for all the 93 requests. And it doesn't matter that most requests are pretty fast. If some are unpredictably slow for reasons, then that translates into slower service to the user and a degraded experience. So the problem here is that time is a resource, and we are not controlling our use of that resource very well, or we need to control it to avoid too much variance in the latencies, to avoid the long tail of latencies. Here's a graph of server response times over time, unrelated to the search query graph that I just showed. But the graph shows the response times for a number of API endpoints. And the responses are a bit all over the show, but what is particularly odd is the latency spikes in update credentials. I can't tell you the cause for these spikes, nor does it matter. It could be anything at all, like data compaction, like leaking file handles, and running out of memory, and forcing a computer restart, or quite simply a garbage collector making a sweep. And that's the point. Any of these possible causes are cases where we are not controlling very carefully when some resource reclamation occurs. And instead of managing resources carefully on the fly, we are knowingly or unknowingly letting resource management debt accrue over time. And then some automated process pays off that debt for us. And sometimes it can do it at the most awkward times. Okay, so how do we get a handle on this? The first problem that we have is that we want to avoid holding system resources like file handles, like sockets, database handles, etc., for longer than necessary. Even if we do release some or all of these resources back to the operating system eventually, releasing them too late runs the risk of having us blocked or killed by the operating system because we exceeded some quota. For example, on Linux these days, the default is that processes are allowed to open 1,024 file descriptors at most, and that includes sockets. So the second problem we have is that memory management can be expensive. It takes time to find a location in memory, to allocate objects, and it takes time to automatically find what objects can be freed, the way garbage collectors do. And again, we don't care about the amortized cost of garbage collection over the entire runtime of the application. That might be as low as 5–10% overhead if you can find the right GC parameters. The problem is that GC sweeps are not always instantaneous, and when they're not, you'll see spikes in latency. And latency spikes in one place can severely degrade the performance of the system overall. So let's focus on the first problem, and then we'll talk a little bit about how that what the picture looks like in the for the second problem. A lot of what we do is implement network services interacting either with other services or with a user's browser. And these are long-running processes. So it's important to ensure that they don't leak memory and that they don't leak anything that was allocated to them by the operating system, like file handles to read or write data, like sockets to create connections, and connections to send messages to other services. And so actually we want two things. We want any resource claimed from the operating system must be released back to the operating system in a timely manner. And any resource released back to the operating system should never be used again. A common problem is that we get a hold of a new connection, and so let's say every time a client connects to a service, and we expect that to happen thousands or millions of times without the service crashing. But if we forget to close the connection, then we're leaking the underlying file descriptor provided by the operating system. And the operating system will only give us so many file descriptors. We said that typically they'll only give us 1,024 at a time, according to the default parameters on Linux. And so we better use file descriptors parsimoniously, because otherwise the operating system might think we're misbehaving and just refuse to give us more file descriptors. So here's a screenshot of a patch that was done a few years ago on a system that's called Ganeti, and it's a virtual machine cluster management tool that was originally developed by Google. And it consists of a number of services, including a configuration service that clients connect to. And here's a bug fix. So the client, this is a bug fix to the client code, and that was mentioned in the release notes. They were opening a socket to send UDP messages somewhere, and they were never closing the socket. So anytime they queried a new server, a new connection would be created and never closed. So the fix was to surround the network interaction code by a so-called bracket. Brackets are a common pattern in Haskell. The bracket function ensures that initialization and cleanup of a resource happens before and after executing the provided action, no matter what. And even if the thread is interrupted by a synchronous or asynchronous exception, and yet, clearly there was no static check forcing us to use the bracket here, and indeed, the original code didn't use it. In fact, this bug that's being fixed by the patch that you see here survived 2 years before being fixed. So arguably, this is an API design issue. And one way to avoid bugs like these is to bake in the bracket pattern into the API. So to say what I just said slightly differently, what we could do is to make any function that allocates a socket into a function that also frees the socket. And so to the left here, you have the original socket API. So you have the socket function to create a socket action to create a socket. You have send to. Of course, you can also receive data from a socket, but we'll ignore that for the purposes of this conversation. And then, crucially, sockets are system resources that need to be disposed of at some point. And so you have a close action. And so what we can do is introduce with socket. And the idea is that with socket kind of replaces both the socket function at the top on the left and the close function. And you give it an address to bind, and then you give it a function that says, you're given a socket, here's what we're going to do with that socket. And then once that function is done running, then with socket will just close the socket. And so with that, there's no way that you're going to forget to close the socket the way we saw was the case for 2 years in this system that was in production called Kinetti. And so if the problem here is that you might have to open a number of sockets, and that might mean, so if you're acquiring a number of resources, you're going to need to nest these calls to with socket, and that might make your code pretty unwieldy. So what you can do instead is to introduce a socket monad and make it such that the socket creation function can only be called when in the monad. And when the monad is run, then all sockets that are created get destroyed in one go. In fact, this is exactly what the popular ResourceT monad transformer is about. The ResourceT monad transformer can also be nested to create an arbitrary number of scopes. And if you want some resources to be, released sooner.
Excuse me, Mathieu.
Go ahead.
Sorry to interrupt. I think there's a slight presentation problem where the bottom.
There you go. Okay. Well, the crucial function was run ResourceT right at the bottom, and that was being obscured. Sorry about that. Much clearer now? You don't see the controls anymore? Okay.
All good. Thank you.
Excellent. All right. So the ResourceT monad transformer can also be nested to create arbitrary number spokes, so this is this is a fine solution. It's what people do at this point. But note that this is not a complete solution to the problem. Not only do we want all sockets that get created to eventually be destroyed and be destroyed exactly once, but we also want to make sure that sockets do not get used after they get destroyed. And so, for example, we may want to make sure that we're not calling send-to on a socket that has already been closed, because if we do that, that will raise an exception. And if this exception isn't handled properly, then the whole program crashes. So in other words, the bracket pattern or the ResourceT monads are only a partial solution to the resource safety. They provide a guarantee that resources like sockets will eventually be destroyed, but not that they won't be used after being destroyed, or indeed destroyed multiple times. So this is an example of code using ResourceT. I wrote the function socket so that once I get to the end of the scope introduced by the run ResourceT function, the socket will be closed. But there's nothing stopping me from writing send-to right after that block of code. This still type checks, even though the socket has been closed at this point. The resource has been destroyed. So how do we achieve full resource safety in Haskell? The key trick that we'll see in a moment is to track in the type system how many times a variable is used in any given lexical scope. And the way to do that is with the new linear types extension that my colleagues at Twig developed over a period of 4 years now, and that shipped as part of GHC 9.0 earlier this year. So here's the current API for sockets. And the first change that I'm going to make is treat sockets as stateful objects and actions on sockets as things that can take a socket in one state and return a new socket in a new state. So here, send-to now returns a socket where it used to return nothing. And if you, yeah. And so now the problem with this change is that there's nothing stopping us from reusing old sockets. So the idea of this API is that when you're performing multiple send-tos one after the other, I write code like this. But there's nothing preventing me from writing this instead, where instead of properly threading the different socket variables, where I first use S0, then S1, then S2, and each variable gets used exactly once, here I end up using S0 twice. So the second change that I'm going to make is to annotate some arrows, specially, to indicate that the actions are linear in some of their arguments. And I then need annotations to do the opposite. And in the case of implementing receive, but we're not going to look at that right now. But the crucial thing that we need right now is that we need the API to enforce that we're using the socket variables in a do block exactly once each of them. So this is still not enough because we designed the linear types language extension such that when in the legacy IO monad, linearity annotations can be pretty much ignored. And so we introduced a new monad that we defined in a package on a package called linear base, and in it you'll find a new monad called Rio. And we made it so that, so for the purpose of this talk, you can think of Rio as just the IO monad, but a resource-aware IO monad where the linearity annotations crucially do matter. And so with these three changes in place, I now have an API that enforces resource safety. There's no way for me to forget to close a socket after I opened it, because in the context of the Rio monad, if an action returns to me a socket and I don't use it exactly once, then that's a type error. So here, S2 is never used, and that's a type error. There's no way for me to reuse a socket by mistake, because doing so would mean using a variable twice, hence not exactly once, and that would be a type error. And likewise, there's no way for me to use a socket after it's closed, because again, this means using a socket twice, which would be an error, since the types are telling me that specifically in the context of the Rio monad and other linear contexts, all sockets must be used exactly once. And even better, I'm not forced into a nested discipline of resource management. This API does not force me to clean up sockets in any specific order. I can open a socket, then another, and close the first one before the second, or the second before the first. It doesn't matter, so long as they all do get closed eventually. And in our experience, this kind of freedom is I mean, it's not actually all that crucial for network code, but it's very important when the resources we're handling are not sockets, but objects in a secondary or foreign heap. So let's talk about that next. But before we do, I want you to keep in mind the words of John Hughes in his seminal Why Functional Programming Matters paper, which is now 30 years old. John Hughes extols the virtues of modularity. He says, when writing a modular program to solve a problem, one first divides the problem into subproblems, then solves the subproblems, and finally combines the solution. The ways in which one can divide up the original problem depend directly on the ways in which one can glue solutions together. And then he says that this is the key to functional programming's power. It allows improved modularization. It is also the goal for which functional programmers must strive: smaller and simpler and more general modules. So we'll come back to that in just a moment. All right, so the other use case that I want to talk about is high-performance language interop, because this is where you're going to see that nesting, using, for example, the with socket pattern can really be a cost when I'm dealing with other types of resources than just sockets. So something my colleagues at Twig and I have been focusing on since the very early days is high-performance language interop. And we did this because we believe that re-implementing the entire world in Haskell could be a fun hobby, but it's a futile endeavor. We're not particularly interested in making our solutions all Haskell all the way down. And in fact, for all our love of Haskell, we love other languages too. And we're not afraid to reach for Python libraries for numerical analysis, R libraries, or for R libraries for statistics and visualization, or even to reuse some of the many high-quality distributed computing frameworks from the JVM. And so I think that increasingly will be no such thing as big code bases in a single programming language, and increasingly we're going to want to reach out to existing high-quality components in other languages. And in fact, everyone has been doing this for at least 20 years. And with Haskell 98 supporting, specifying an FFI. And I mean, in practice, the amount of C code leveraged by production Haskell code today is rather large. I mean, typically we're using OpenSSL, we're using zlib libraries to talk to databases like PostgreSQL and more. So in 2015, we released a thing called Haskell R, which allows us to interact with the R interpreter. In 2016, we did the same thing for interacting with the JVM, and a lot of other people have been implementing similar bridges to Rust, to .NET, and a lot more. And the problem with doing all of this is that a lot of these languages are garbage collected languages. And that's a pretty dangerous state of affairs, because you then end up with having two heaps. And so in the case of Java, garbage collection is done by the JVM's GC. And then Haskell itself is a garbage collected language, of course. And so normally the JVM's garbage collector is the only garbage collector in the entire process, and has a global view of the heap. But now we have two heaps, and so neither the JVM garbage collector nor the Haskell garbage collector have a global view of the heap. And this is pretty dangerous, because we can't let either garbage collector cut the grass under the feet of the other. Take, for example, this simple scenario. We have an object in Haskell pointing to another in Haskell in the Haskell heap, as well as an object in the Java heap, two objects in the Java heap. And the JVM garbage collector could believe that, for example, one of these objects is no longer reachable, in which case it gets deallocated, and then we're left with a dangling reference to uninitialized memory on the Haskell side. And so if we dereference that, we could end up with a segmentation fault. So we really need to essentially register any pointers that we have in the Haskell heap pointing into the Java heap. And so basically what we need to do is that we need to add those pointers as extra roots for the Java garbage collector. Okay. So the JVM's foreign function interface is called the Java native the JNI. And as it turns out, the JNI does have facilities for adding these GC roots. And we basically have facilities for adding two types of references. One is global references, and the other is local references. And the global references are really slow, and the local references are much faster. And so you really want to be using the local references pretty much all of the time. So let's say that I write Haskell code that allocates a new Java array. And so J here is the type of references to Java things. And here I have a reference to an array of Booleans. That's what the type is saying here in purple. And so at some point, I'll need to tell the JVM that I'm discarding that reference that I'm calling X's because it's a garbage collector root. And so if I don't do that, then the memory of the array will never be reclaimed. In other words, we're facing a situation similar to the early one. A third party, in this case the JVM, and in the previous case it was the operating system, handed us a resource, and we need to manage the lifetime of that resource somehow. So one way to do this is to add a finalizer to the reference instead of having to say, for example, delete local ref manually. Delete local ref is the thing that removes the GC root. But then we have no guarantee of when that's actually going to happen. And worse, we actually have to use, we can't really use local references for this because the finalizer could be run in any thread. It might not be the same thread as the thread in which we created the reference. And so, yeah, we need to use global references, and global references are a lot slower. And the JVM really encourages you to use these local references instead. So the one solution here is do the same thing as we did with sockets, right? We could be tempted to reach out for the same tricks as before. We could use the with pattern to never create a reference without also deleting it eventually. But now I want to show you a more complex example. So now I have a stream, which is at each step, it's calling the next method of the Java iterator and getting a local reference to some object in return. That's the point at which the resource is acquired. And then I have an action that processes that object somehow. And that action must delete the original reference, otherwise we'd have a memory leak. And moreover, if the processing function deletes the original reference, then we are discarding references on the fly as we are mapping over the stream, rather than accumulating references that at best we'd be deleting in one fell swoop later. But now the place at which I'm creating the reference is separate from the place at which I'm deleting the reference. And I can't make them be at the same place without getting rid of the stream abstraction. To illustrate what's going on, let's unpack the streaming abstraction and partially evaluate this code. Let's assume that the original array is just an array of 2 elements. And so morally what's going on is that we're calling the next method of the Java iterator twice. Then we're passing the resulting object to some action. And then after that, we're printing the result. So the resource is being acquired in next, and then it must be discarded by some action, because otherwise there's a leak. And so let's zoom in even more closely into some of the code here. If this was Rust code, the next method would be moving ownership. If this was Rust code, the next method would be moving ownership of the reference out into the context, and then ownership would move into some action. And if some action doesn't return the reference, then by the Rust semantics, the reference would be automatically and forcibly destroyed because it is not moved anywhere. So there's no room for error. But Haskell is not Rust, and so we have to do something else. And applying applying the with resource pattern, the only thing we can do here is use the with combinator. The reference is acquired with next, used in some action, and then deleted with the with Java combinator. And so, in short, instead of using bind, which is the standard glue to compose actions, we have to use some other bespoke glue here. And in so doing, we're losing all the abstraction that was built using bind. So set in the framework of John Hughes, next and some action are not independent modules. Implementation details of both leak out into the context and forces us to use a special kind of glue. So rather than bind, which is standard 1, we're effectively using with Java object in its place. Whereas with linear types, we can model something similar to the move semantics of Rust and ultimately avoid the implementation details leaking out. With linear types, we can combine actions using monadic bind, like we do everything everywhere else. It doesn't depend on it's not because of some implementation detail of what's to the right of the bind and what's to the left of the bind that all of a sudden we have to say, ooh, well, these 2 things that I'm trying to compose don't compose with bind, they can only be safely composed with this other combinator called with Java objects. So we're using this other combinator just because of implementation details of these two components. So coming back to our two problems, it sounds like with linear types, we now have a solution to our first problem, namely avoiding resource leaks without running the risk of seg faults, and a pretty general solution at that. And it's one that scales up to handling resources in a way that doesn't force us to give up existing abstractions. And so the second problem is really the other side of the same coin. So let's talk about that for a little bit. Memory is a resource like any other. And so traditionally, we've had languages split into two camps, the GC and the GC languages and the system languages. With and the problem is that the languages with that are garbage collected might be pretty slow, and so we might get latency spikes like we saw earlier. So take this, for instance, a post published by Pusher in 2016. They're implementing a service in Haskell, and they have a service that conceptually is an in-memory message bus. And new messages get pushed on one end, and old messages get popped out at the other. And if we look at the thread scope graph here, the pink lines show when a message comes in and into the system. So basically, whenever there's pink, there's productive work being done. But you see that there's not pink everywhere. And where there isn't pink, it's because there's a garbage collector doing stuff. That's the orange that you see over there. And so that means that the 99th percentile latency for this service is pretty poor, of the order of several hundred milliseconds or more. And so that's potentially money lost for someone, as we mentioned earlier. And these latency spikes are caused by the garbage collector. But crucially, they're long spikes because there's a lot of objects that are long-lived in memory. It's not because we're allocating a lot per se. It's just that the working set is very large every time we do a major garbage collection sweep. And so that takes time. And so one idea here is to basically split the heaps into two heaps and to have one long-lived heap in which one heap that's specifically for the data that is long-lived. And so in this case, it's the messages that we're keeping for a very long time in the message bus. And then everything else that are basically scratch allocations, objects for allocations that happen during serialization and deserialization of the messages, for example. That can all go into this miscellaneous heap, which is managed by the GC, whereas the message heap is uses explicit allocation and deallocation. And so we might be because the allocation deallocation is explicit, we want to use linear types here to make that safe. So in many ways, adding linear types to Haskell has been an exercise in stealing some of the DNA of Rust and sticking it into Haskell. And so Rust has stellar facilities for handling system resources and fine-grained control of memory. And now Haskell has something like it too, but one question that might have been wondering about for a while now is why Haskell? Why do all of this in a functional language? The linear types work started in 2016 when Twig started an engagement building software that where the latencies really matter a lot, like in the search engine use case, because we were building software for so-called exascale supercomputers, and that's to say computers with 1,000 petaflop compute power, or 1 exaflop, and 1 exabyte of storage capacity. And a lot of the tasks that are running on these these computers are bulk synchronous tasks. They need to run. You need to run each step in exactly the same amount of time before they synchronize across all tasks. And so why did we insist on building software for the high-performance computing industry in Haskell when we could have used C or C++? Well, it's precisely because us dirty and unwashed industrialists found John Hughes' argument convincing. The argument that taming software complexity has a lot to do with being able to compose building blocks using basic glue. Yes, we do want a programming language that lets us represent system resources using non-leaky abstractions. But we also want that programming language to let us assemble building blocks through simple functions, simple functions and simple function composition, or monad bind. And to mention Rust again, in Rust today, concepts like functors and monads are pretty awkward to define and use. And in Rust, everything is a resource in that everything has a lifetime, and I have to reason about those lifetimes in my code. They appear in the types, and I have to think about them anytime I call a function or even define a variable, because I often have the choice of allocating on the heap or allocating on the stack, and these are all kinds of questions that I don't really need to ask in Haskell unless I specifically opt into all of that. So we thought that it was important because, in my experience in software and building software, you want to be able to iterate fast, and to iterate fast, iterating fast that gives you the ability to explore quickly a design space and backtrack often. And you need to be able to write code that you can refactor very quickly. So we turned to Haskell for all the usual reasons. Easy to refactor, and then of course when the code, we used Haskell to build prototypes. When the code grew and became less of a proof of concept, we were glad resources were modeled accurately because with no hidden gotchas, because then we could push that into production and things just work. And so it was very nice to be able to have fine-grained control over performance characteristics of a program when needed. Of course, at the time, linear types didn't actually exist, so we had to pretend that they existed. But now that they've shipped in GHC. And everything I just said counts double when you're writing correctness critical code, which is the other reason to use Haskell. So like in finance and biotech, or writing embedded devices, or embedded software for autonomous cars or autonomous planes. So to summarize, I believe that functional programming matters to us industry users. And in our work, we have to deal with the spleen of computers. And they're pretty messy and complicated. Linear types give us the means to model the essential aspects of the things we're dealing with, and to take the idea of a socket or the idea of a file and express the relevant aspects of those ideals in the abstractions we write as code. Functional programming with linear types, we can still have, with functional programming and with linear types, we can still have all those abstractions, like monads, like applicatives, and so on. And in reality, everything is a resource, of course, but we can selectively expose that reality while programming and hide that reality when it's not relevant. So I focused in this talk on the application of linear types to resources because that's perhaps the most salient angle from an industrial user's perspective. But linear types can bring a lot besides, like a pure interface, immutable arrays, the ST-monad, quantum computing, all things that are going to be discussed, presented later in this conference. So leave it to Jean-Philippe tomorrow and some of the other speakers to talk about that. So yeah, thank you very much for listening, and I look forward to any questions if anyone have any. And we still can't hear you.
I suppose if we can't hear Yuriana, I can chair the question period. So let's see. There is currently one question here in the queue. Here comes more. But first, I'm going to call on Gergo. So I'll just read this one off. Why doesn't or can't RIO just replace IO? Why do we need a separate type?
So in principle, it could, but if we did that, and in fact, so the system that was designed that was published in the linear types in the Popple paper that presented linear types in 2018 includes multiplicity polymorphism, and it's designed in such a way that you could use Rio as just the IO monad, and everything would just work. The way the Rio monad is implemented today in linear base does incur probably a little bit of overhead, although we haven't really measured that, but it incurs, in principle, a little bit of overhead relative to just straight up I/O. And the reason for that is if you want Rio to really be a correct abstraction for a resource-aware monad, then you need to be dealing with all of the vagaries of Haskell. And in particular, in Haskell, you have such a thing as asynchronous exceptions that could be sent to a thread, or synchronous exceptions. So when those exceptions happen, you want things to be deallocated. You want things to be deallocated even as you're unwinding the stack. And so we basically do some extra bookkeeping right now in the Rio monad in order to deallocate in all circumstances. But this is a minor implementation detail that might not matter to the community, and so indeed, maybe we can just redefine IO to be Rio.
Great, thanks. And that question was from Gergo Erdi. Mark that as answered. Okay. Next question I see here is from Dominic Orchard. Do you envision a route for these ideas to make it into other, quote, mainstream languages?
So I think that the ideas here are, they were developed in the context of one particular programming language, and a functional one at that, Haskell. But I think it's at least applicable to most other functional programming languages. And but beyond that, we just haven't really thought about it very deeply when it comes to say more imperative languages. And I would say that for example, the solution that Rust has is quite different from this one, but it works extremely well in the context of Rust. It works extremely well in the context of Rust because Rust is an imperative language, and the goal of Rust is just make the imperative style safe. Whereas Haskell is just, it's very different type of code. So I'm just not sure that we can say, hey, here's a new invention, let's use it like a hammer and go apply it everywhere. I think it's relevant for a number of other functional programming languages. I'm just not sure about the story in imperative languages.
Thanks. Let's see, we'll mark that answered. So this question is from Ryan Newton. Of the potential future work remaining in linear types, what do you think is most important? 1, linear constraints. 2, supporting linear let bindings. 3, something else.
So number two is something that's pretty important, but it's not too difficult. We're basically there as far as I understand. But linear constraints is the one thing that I'm particularly excited about, because if you look at the, for example, the socket code that I showed earlier, I said, hey, look at that. It's great. It's resource safe. There's no way that I can call send to after I closed. There's all kinds of bugs that just disappear. And as I was showing before that, these bugs do exist in practice, but now they've just become impossible. That's a great promise, but it comes at the cost of having to come up with all these fresh names all the time for any time I interact with my socket. And that's a real downside, very practical downside and so it means that in practice, when I'm writing this network code, it's just going to be a lot more annoying to do it with the safe interface that I was proposing relative to the original interface with sockets. And so linear constraints is one possible solution to basically get away from that tedium. So I think that with the linear types that we have in GHC 9.0, we have the basics to allow you to write code that's resource safe, but we don't it doesn't mean that the user experience is going to be particularly great at this point. And then I think that linear constraints, is going to be what's going to be really key to getting the user experience to a much better place. And something else that I would add here is that Rust has been doing this for a while, and every iteration of the Rust compiler, every new release, have been a lot of improvements to the user experience there. And so I think you're going to see a similar thing happening with GHC, where with every new GHC release, we're going to make it, we're not just going to focus on, hey, let's enable people to, in theory, write resource-safe code. We're also going to make it easier for people to make it convenient for their users to write code that have linear types in their APIs.
Thanks. This one is from Eric Gorelick. As you say, most languages are cleanly divided between systems and GC'd, with not a lot in between that could be used for applications like soft real-time. Do you think linear types could make Haskell be the language of choice for such applications?
So I think, you could have designed. This is not inherent to linear types. You could have designed Rust in pretty much the same way that Rust is designed today. But for example, I don't think that it was necessary to give all these very strong guarantees in the semantics of Rust that make it so that the compiler is exposing to you whether it's going to allocate things on the stack or whether it's going to allocate things on the heap. You could imagine a kind of pared down Rust and maybe this might be the future for Rust, where you do have a garbage collector, and so then sometimes you use the garbage collector, sometimes you don't. And the design that they would have there wouldn't really use the linear types as proposed here. But indeed, I think that for most applications, the future probably is a language where not everything is a resource, but some things are resources because you want them to be resources and you want to expose that reality. And then for the rest, you don't want to. I very much believe in that middle ground between, say, today's Haskell and today's Rust. I just want to point out, and linear types is one way to get to that middle ground. I just want to point out that there are other ways to get to that middle ground too.
Next question here is, I think it's a follow-up about the RIO versus IO. or maybe not. Maybe it's not a follow-up, but it's also from Gergo Erdi. How can you deallocate if close is now just a random but linearly typed function?
I'm not sure I understand what random means here.
So I'll invite Gergo to the stage. I know earlier he didn't have a mic, but maybe he does now.
Yeah. Can you guys
Okay.
hear me now?
Yeah,
Yes.
we can hear you.
Yeah, so what I meant is that, yeah, when you were talking about RIO, you said that it has to be prepared to deallocate resources even in the face of exceptions. But the whole point of the socket API that you showed us was that, there's no with pattern that would connect the close function to the creation of the socket. So it seems to me that we now have a random function that just happened to be called close, and it happens to close the socket, but it's not connected to the socket itself. So what does RIO do if there's some exception coming from somewhere?
Right.
I'm just not seeing the connection here.
Yes. You can imagine that the ROA is going to expose some primitives that are not otherwise available to the user of the socket API, but are available to the implementer of the socket API. And so then the implementer of the socket API is going to use these primitives to say, hey, this is close. And close is not just a random function like any other. It's a function that does something special to resources. And so, the answer then, I guess, is no, close is not a random function, but because it's implemented using a little bit of magic, but that magic is not part of the socket API, and so isn't a problem for the users. It doesn't break the guarantees for the users.
Does that answer your question, Gergo?
Well, it does, but I feel like I would need to know more details to form an informed opinion about it. So yeah, I'll take it as an answer. Sure, thanks.
Happy to discuss more in the lounge if you like.
Okay, let me remove Gergo from the stage. And then looks like this will be the last question from Adam Gundry. Another way to handle the long latencies caused by GC pauses is to use a low or no pause GC algorithm. For example, the non-moving GC in recent GHC versions. How would you say this compares to the linear types approach?
I would say all the more power to users. This is great. I think that there's no, let's take, for example, take the pusher use case. As I said, there's multiple ways to skin that particular cat. And so, one way is to use linear types, but there were other routes possible there. And for example, if the blog post, they wrote a blog post, and the blog post I was referring to dates back to 2016, which is before the new GC, incremental GC, made it into GHC. And it's possible that just by using this new GC, things would have been good enough for their particular use case. And it's possible that there was no particular need then to split things into two different heaps, with one heap that's managed manually and another one that's still managed by the garbage collector. Or maybe they want to push they want to get even more control over the latencies. They want the tail end of the latencies to be even tighter, in which case maybe they eventually do need to move to linear types. It depends on the use cases. It depends on your measurements. It's good to have multiple tools in your tool set to bring to bear when you have a performance problem.
Great, thank you. And we have one more question that has appeared. I do think this is going to have to be the last one to give everyone a break. But let's bring it up here. This is from Artem Penelitson. Judging by the experience in Interest 2, linearity can improve developers' experience and help to synthesize parts of code more effectively than in an unrestricted setting. is Twig interested in working in that direction? For example, extending HLS to support linear types.
So this is absolutely one of the big promises of linear types. So now you mentioned Idris 2, and Idris 2 is a dependently typed language. And one thing I didn't mention, but is worth noting, is that the way we design linear types was specifically, we specifically had in mind when we designed linear types the idea that it would have to be compatible with dependent types down the line, because we're hoping that Haskell will itself become a dependently typed language like Idris is. And something that I can say is that, going back to 2016, when we first started looking at linear types, we were actually wrangling. We were thinking about these pretty complicated protocols, and we weren't quite sure how to design these protocols, and whether what we were trying to do actually made any sense at all. And so part of the reason why we started thinking linear types, and Jean-Philippe and Arnaud Spivak can we're closer to this at the time and can tell you what came first. What was it, the performance concerns, or if it was the aid in the design of the protocols and the design of the code that was more interesting to them. But this was definitely part of the story from day one for us. There were definitely both motivations. I focus more in this talk on one particular motivation, but both do exist. And I very much hope that we can get very nice integration in the IDE experience for Haskell in the future, and with HLS specifically, because I think there's a great promise. And you might have seen some of the videos from Edwin Brady here that show the power of linear types, in particular with regard to code synthesis. And it would be absolutely fantastic to have the same in Haskell, and I see no reason why we would not have that in Haskell 2 down the line.
Great, thanks. Thank you so much for coming to Haskell Symposium. Let's all thank Mathieu again.
Thank you for having me.
We now have, I guess, 22 minutes until the next paper session of the day. So we'll see you back here then. Thanks all.
See y'all.
All right, I'll kindly uninvite Mathieu. We're still here. I'm going to bring the speakers in. Jamie, where are you?
Just so you know, your camera's off.
Yeah. Ah, Jamie's not here yet. Is Nicholas here? No. Okay. Let's hope they show up.